Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, hi everyone. Thanks for coming this morning for what's really a two-part series of talks from Bjorn Hartman and David Mellis. David will be speaking right after this at 11, so I hope many of you can stick around for that. But our first speaker today is Bjorn Hartman, who I think a lot of you know, but for those of you who don't, Bjorn's a faculty member at UC Berkeley, where he does really great work in human-computer interaction and ubiquitous computing. And so we're very excited to have him here today to speak to us about some of his group's most recent work on interactive prototyping tools for the maker community.
Great.
Thanks.
Thank you, Salima, for the introduction. Thanks, everyone, for coming half an hour earlier than you would usually expect for a talk. So over the course of the next hour, I will show you how you can transform a printed piece of inert 3D plastic into a working game controller by adding a super sensor into it, namely a camera. So you add this camera to a 3D printed piece, and you end up with a working game controller. I'll show you new smart prototyping techniques like this augmented breadboard that helps you debug circuits when you breadboard. And I think Rob just had his first breadboarded circuit, so directly relevant to you. And some new types of fabrication tools that we're building, such as this machine for 3D surface augmentation. So not printing from scratch, but working with existing objects. So this is where we'll eventually end up, but let's take a step back and ask why. So talk is titled Interactive Tools for the Maker Movement. So maybe I'll just take it from the top and say, what is the maker movement? Who's been to a maker fair or an event like that in the room? So maybe about half the room. So for me, what's exciting about the maker movement, it's this bottom-up effort to engage people from all ages and all walks of life in learning how our world of made objects actually works under the hood. And so transforming them from kind of passive consumers in that world of goods into active participants. And so this is just a snapshot from a recent soldering workshop in Detroit that shows you some of certainly the age diversity that you have there. I think ground zero for the maker movement are these events, the maker fairs. The first one was 10 years ago in San Mateo, and I just happened to live across the street at the time. So I just walked into my first maker fair, and it has now turned into something that I think this year attracted 200,000 people just to that main event, and there are probably close to 1 million people who attend the associated events, just the official ones, and then of course there are many spin-off events. So if you haven't been, you should absolutely go. It's kind of mind-blowing the first time you're there. So a lot of this happens out open in the community, in hackerspaces and open public events. But I think in addition, we're also seeing hackerspaces and makerspaces appearing in high schools, middle schools, and on college campuses. So this is a picture of the hackerspace of my friend John Froelich at Maryland, and you see actually quite a number of quite high visibility efforts going on, such as the new Innovation and Design Center at Yale, the Invention Studio at Georgia Tech, or at Case Western, the 7-story Think Box that actually now is already getting too small, so they're getting a new building next to it. Okay, so there seems to be a lot of enthusiasm and action around the maker movement, but to me another question is kind of what's at stake? Why would we care? Why is this important to support rather than just a nice activity that's going on anyways? And I think there are a number of different reasons, so let me give you 3. The first one has to do with the nature of our education and what we're training people to do. So I'll let you read this quote from Alan Watts, favorite Bay Area philosopher. And this was written in the 60s, and it certainly still rings true today, that we've seen kind of this alignment, mostly of what we think of education is analytical skills. And that is great. Certainly the students we accept at UC Berkeley are just fantastically prepared in STEM disciplines. But what is maybe lacking is an understanding of how all that theory actually connects to problems they might face in the real world. And we've gone so far down that path that actually I've seen electrical engineering students enter PhD programs who've never held a soldering iron before. So there's an educational objective of kind of connecting, connecting concepts and theory back to what actually tasks that matter. Then there's also an argument around innovation, and Eric von Hippel probably makes that argument the best, which is that lead users who really understand the domain, understand the domain better than companies who come in externally, and therefore are a very important source of innovation. So this book gives plenty of examples from the world of medical devices and sports equipment, where it's the physicians and the athletes who have the insight. And so if you can give them better tools to translate their insight into inventions, then you actually increase the bandwidth of our innovation pipeline. Last argument has to do with the state of manufacturing in the US. So there's this rather gloomy article written 5 years ago, Why Amazon Can't Make a Kindle in the US, that argues that basically we've outsourced now enough for so long that we're not even able to make things in the US even if we wanted to. And the maker movement here is an interesting, maybe counteracting force. So let me give you an example. On the left, you see the Type A machine. This is a 3D printer built by a company in the Bay Area. And they made their first set of printers at local tech shops by laser cutting wood and taking hardware out of the hardware store. And so having access to Makerspace's Fab Labs gave them enough tooling to build something that really didn't look like a finished product, but was actually functional, and they tied into a network of other makers who bought these first machines, and that gave them enough expertise and capital to then bootstrap to turn that into something that looks much more like a finished, robust, mass-produced product. So the White House is paying attention to this. And so in 2014, there was the first White House Maker Fair. And I believe next week is going to be the second National Week of Making, with events in Washington, D.C. and statewide. And I think it's for a variety of these three reasons of education, the innovation pipeline, and strengthening the knowledge around manufacturing in the U.S. that the government is really paying attention and wants to kind of foster this. Okay, so hopefully I've convinced you that it's not just neat activity, but there are some important reasons underneath why we should support the maker movement as well. That still doesn't answer the question, does the maker movement need us as researchers? Right? Maybe they're just fine building their own tools because they're very enterprising people. So if I didn't believe that research had an important role to play, I probably wouldn't be standing here. So let me give you just a couple of reasons. First, what is really interesting about the maker movement is that it inverts the traditional model of education, certainly of engineering education, right? Where the traditional model usually is, welcome, take some math, take some physics, maybe some chemistry, then learn about signals and systems, maybe some assembly, and then you work your way up the step, and before you graduate, you get to do a project that puts all of that together, which basically means that for 3.5 years or so of your undergraduate career, you're wondering, what is all this good for? And so this is really turning it around and saying, no, we'll start with interesting projects in the first place, and then that generates a pull for conceptual knowledge and more powerful tools kind of just in time when they're needed for your project. A second reason is that these projects tend to combine both questions of design, so what is it that you want to build, what should it do, as well as fabrication, how are you actually going to realize it? There is also this new digital fabrication toolset that's emerging that just allows us to, as software people, to really bring our skills into this entirely new space, and that some of the machines really are not that new. They've been around for decades, but it was only in industrial settings for a prescribed small number of industrial uses. And so this exploding number of people who have access to that equipment gives rise to new challenges. And I think just generally amateurs need different abstractions and affordances to be successful than either from novices, who you want to train to become experts in a particular domain, as well as those experts themselves. And so to me, all of these imply a need for new appropriate design tools. Yes?
Can you just quickly say what distinction you're drawing between an amateur and a novice?
So I think of a novice as someone taking CS1, right, who is on the path to becoming a trained software engineer, but is only at the beginning of that path. And so for me, an amateur is maybe someone who is actually not on the path to become a trained expert in that domain, but who wants to be proficient in a tool set because they'd like to apply it to problems in a domain they really care about. So maybe like what we think about as end-user programmers, in the programming world, that has some overlap with this notion of amateur here. So people who program but do it because they want to understand their data or want to automate business processes, not because they want to be software engineers. All right. So one way to organize this, my thinking in this area has been this research theme of understanding what the 21st century workshop will be like for these makers. And when I say workshop, historical examples to draw on are the Wright brothers workshop, who were the first ones to get to controllable flight. And it was their background as bicycle mechanics and manufacturers that really gave them the facility to experiment with building things and mechanisms. And so it was, the 19th century workshop with power tools that enabled that to happen. And then, of course, skip forward, and you get to the famous Garage by Hewlett and Packard, right? And it was the emergence of vacuum tubes and transistors and integrated circuits that gave them the material to build instrumentation and later information appliances. So what do I think the core ingredients are of this 21st century workshop? Well, it's powerful design software combined with digital fabrication tools and combined with ubiquitous, basically free programmable electronics. Design software, of course, enables users to create detailed plans and specifications and code how their creation should look like and work like. And this is where a lot of my own work as a computer scientist comes in. We create the software that lets users create these models and plans. Now, the second important trend here is I don't think there's quite a Moore's law of industrial fabrication, in that it's quite a bit slower. But we've seen this trend of certainly the price and the size of equipment to make things dropping by several orders of magnitude. Now, where the analogy a little to Moore's law breaks down is that desktop fabrication is not as powerful as industrial fabrication, right? There are many processes that still only exist at industrial scale. But I think the same force of democratizing access to tools and having a much wider variety of people have access to these machines in their home, their lab, or maybe the hardware store in their town. I think that's the powerful theme here. And then the last ingredient here is, of course, ubiquitous programmable hardware, in that you can get microcontrollers for sense, and you can probably by now run an operating system and have a radio for $1 or $2 in your product. So we've been experimenting with how this 21st century workshop should look like and what people would do in it in the Jacobs Institute for Design Innovation. So this is a brand new design institute that we opened at UC Berkeley last August. So we only have 2 semesters under our belt. So everything I say about it subject to change and might sound quite different next year. We're focused on undergraduate education. So undergraduate, maker-centric, design-centric, team-centric, open-ended projects happen in this building. We have 3.5 floors where some of the floors are dedicated to teaching. So Berkeley is a big place, so our classes come in quanta of 50 students. So a small class is 50, slightly larger is 100. If you take Intro to CS, it's 1,500 students. They don't fit into this building. And then the entire first floor is kind of an open makerspace fab lab that's never reserved for classes. And then we have various digital fabrication equipment sprinkled throughout the building, kind of separated according to functionality, so you can give people different access to those different tools. Here's just a shot of what our first floor makerspace looks like. So on any given day, you might find people working on CNC cut furniture, as well as mill circuit boards populate them, work on electronics. And all of the classrooms are also kind of flexible with power from the ceiling, so you can actually do actual work on your desk and kind of have everyone huddle around. So in the first year, we've had 15 different departments come and offer courses. We have a program by which Berkeley departments redesign their courses to be more design and maker-centric, so they can then move into Jacobs Hall. We've had 50 courses come through, trained about 600 students per semester on safety training for our machines, and there were actually 3,000 enrollments. So we went from, well, within, I think, 2.5 years from just planning that we should maybe have a building like this to operating at quite large scale. So I just want to give you some examples of the types of projects that students work on in the Institute. Maybe that'll, because I think maybe some themes then will emerge. So on the purely mechanical side, we have students work with the Enable Tech community on building custom DIY prosthetics, low cost. And so these don't yet match in terms of performance or weight what you would get out of medical prosthetics. But the crucial difference is that they involve the kids who wear them in the design process. And so there can be much greater sense of ownership and pride of, I made this thing, this is my superhero hand, rather than the doctor gave me this beige contraption I have to wear. Now, getting a little bit more into what a lot of our projects are, they live at the intersection of, there's some mechanical design, there's some electronic design, there is software design, and then there's a user interface design somewhere as well. So in California, we have a drought. It did rain a little bit, but that didn't really abate our problem this winter. So these students built a fixture-level water flow meter. So running a power cord into your shower is probably not a great idea. So one of the core questions here was, how do we build something like that that's totally self-contained? So they 3D printed this impeller that goes inside the tube. It has magnets on its periphery. Water rushes through, it spins up, induces a current in a coil that's wrapped on the outside. That current is enough to fire up a microcontroller that uses Hall effect sensors to sense how fast the impeller is spinning, and then uses a low-energy radio to send that to a smartphone. And this is actually, right now, this was first a class project at Berkeley, and then we had tech transfer across the bay to Stanford, where right now it's deployed in their dorms. Here's maybe a little more whimsical project. This is a rocking chair that generates power to charge your phone while you're rocking. And What I like about this project is once again, this intersection of different disciplines that all find expression in the final outcome. So someone learned welding to make a frame that could actually support a person. Someone got good at woodworking, doing the complex angles, that were all driven by the goal of having something that's aesthetically interesting. Then the students talked to an energy harvesting expert to think about, well, what is a good way to harness the energy of sitting, rocking? And so he said, you want to have a swinging pendulum that's hooked up to a generator. Then they did the electronics, and there's an e-ink display in the armrest that shows you how much you generate. One last example from the medical domain, because I know there are quite a number of people here working on new medical devices. And here we see, so Berkeley doesn't have a medical school, but UC San Francisco does right across the bay. And there's kind of a never-ending flow of ideas that physicians and practitioners have, but that mostly don't get implemented because right now they lack the tools and local engineers to do them. So if we can lower that barrier, I think we'll see a lot of innovation. So this is a fairly simple device, but can have a profound impact. So sensory ataxia is a condition where you lose feeling in the nerve endings of your feet due to diabetes or other age-related illnesses. And if you've taken a class in controls, if you walk without feeling in your feet, you basically walk open loop. And so people start falling. They become very unsteady in their gait, and that becomes a big complication, falls in old age. So here the idea is pressure sensors in the sole of your shoe just wirelessly transmit a simple footfall signal 3 feet up to your back, where you wear cell phone vibration motors on the sides of your back where the nerve endings still work perfectly fine. And in early tests, this has shown within 10-15 minutes, patients are able to, reintegrate that new information, and their gait becomes steadier from having that simple feedback system. So those are the kinds of projects that are now all within the realm of students completing within 10 weeks or so, and it's this intersection of aesthetics, mechanical, electrical, and embedded and interaction design that all come together. So let me shift now from kind of the larger motivation and all of the things we do that kind of contribute to the research agenda, but are maybe not research in and of themselves. So as I mentioned, all of this activity to me kind of raises the importance of researching new design tools. So I just want to show you a couple of examples of work my group has done in 3 different research areas trying to envision future design tools for this general space. So I'm going to talk first about prototyping tools for interactive devices, where we're trying to come up with techniques that let you rapidly explore what a new interactive device would feel like without necessarily using the implementation tools you would for the final solution. Then I'll tell you a little bit about learning and debugging tools, and if there's time at the end, we'll see there's a third area of kind of hybrid fabrication tools, trying to think what lives in between the hammer or the motor on a stick that is a drill that you pick up at Home Depot on the one hand, and a fully automated CNC robot like a 3D printer on the other hand. All right, let's just take that from the top. So in the realm of prototyping tools, our guiding research questions has been, how can we make hardware prototyping as fluid and as flexible as the prototyping of graphical user interfaces? Because certainly in the latter area, we've had decades of great tools, starting with HyperCard and now going into Framer and mockups and all the dozens of tools that let you quickly mock up user interfaces. Well, first, so we're going to focus here in this section on interactive input devices, so things that take human action and translate that into controls for a game or for music playback or for flight control. And first of all, I believe that even though now we all carry shiny flat pieces of glass in our pocket, at the same time these input devices aren't going away, because fundamentally hand and brain co-evolved, and so there's always a strong case for keeping some tangibility in our tasks, especially when it comes to virtuosity and performance. Now, if you're here at Microsoft Hardware, you might prototype your next game controller by 3D printing what the possible shapes could look like. The fundamental limitation here, though, is that that's just a piece of plastic. It gives you some sense of the aesthetics and the ergonomics, but it doesn't work. If you want to create something that actually works, right, well, then we're talking about electromechanical co-design. Suddenly, this design task is a lot more complex. It's not just what's the shape of it, but where can I fit a circuit board in it, and where can I place components on the circuit board that kind of pop out at exactly the right location. And so this is really the realm of detailed CAD design, where you can spend hours, days, weeks, months into getting the details right. And in general, in prototyping, right, when ideas are still at a more ambiguous stage, we don't yet want to commit the time and resources to figuring out all these detailed design decisions. So we've taken a couple of stabs at addressing this problem. I'll just do a quick rundown of some of them. So a first idea was, well, what if we just keep you in really rough physical prototyping materials, tangible modeling? So could you create working interactive devices through tangible modeling? So we ran a formative study that suggested that, well, some things are easy for people to express through modeling, such as the general overall shape and maybe how a phone holder might cradle the phone. Other things are quite hard to do with modeling material if you're not an expert sculptor, like expressing where a joint is, where something telescopes, or where other interactive functionality is located. And so what people usually do then is there's a mix of, I'll express some things tangibly, and for others I use annotation. So I may just draw a sketch and describe in words what I want different pieces to do. So we use this as inspiration to build a system called Maker's Marks, where the idea is, if I give you tangible modeling material, and then in addition, I give you a suitable set of annotation tags that let you express functionality, then probably you can build something that combines, has shape intent expressed through clay and functionality intent expressed through these annotation stickers. And then if we take something like .NET Gadgeteer, like a standard set of electronic components, and these kind of map onto those, then maybe we can help you with the detailed design task of saying, let's make something of the shape that you indicated that has all of these actually functional components inside. So here's the rough workflow. So you start out by creating one of these models, and then you 3D scan it. So that now gives us both the geometry as well as texture images of your creation. And then we take the set of annotation stickers that we know, that's the library of things you can use, and we basically do computer vision on all of the texture images and try to find whether you used any of the stickers on your prototype. So we find those in the 2D images, and because we know how the textures map onto the 3D models, we can project that back into the space of the 3D scan. And then we basically want to replace that sticker with suitable geometry that allows you to place an actual component in that spot. So then we have a digital model of that component that we can now orient in that 3D space of our scan. We can check whether it actually fits, and then we can automatically synthesize geometry to kind of snap that in place. So basically what we do is we take your model, yes?
What if it doesn't fit?
If it doesn't fit, then either we tell you we cannot work with it, or we actually modify the model and we take your 3D geometry and we push it out from the center. So for example, if the joystick is too big, you'll get a little bit of a bulge in the back of it to house it. So we take your model, we shell it, we add all these cutouts and fasteners, which kind of requires that for each of our components we have this additional metadata. Then you print it out, and then afterwards we basically have these snap fit hooks. So you just snap every component in place, and then you end up with an interactive object. So the programming itself of it is not handled by this tool, but this is what projects like .NET Gadgeteer and Arduino and others, right? They address lowering the threshold for doing that. So the key idea here is that a maker expresses shape intent through sculpting and functionality intent through this placement of stickers or marks. And then our tool handles the detailed geometry modification. All of this does rely on having this database of CAD information about each component available. And so one question is that actually reasonable to expect, or is that a deal killer? Well, it turns out there's one group that has a really vested interest in creating those models, and those are vendors, wholesalers. So McMaster-Carr is the biggest supplier of hardware for mechanical engineers in the US, and literally everything they sell has a CAD model associated with it. So it just basically means augmenting that CAD model with a couple of extra pieces of metadata. All right. So that was the first step of printing interactive devices. Second approach, we were wondering, well, with the advances in 3D printing, can we maybe just, instead of taking pre-existing pieces and then wiring them together, can we just maybe print all of the connectivity in the inside of objects? So, a very simplified example might be maybe you want to make this interactive bunny that has a capacitive sensing on the tail and zombie eyes that light up. Can we just print this in one go, and then you just stick all of your electrical components just on the surface in the end? And so basically, the idea here is printing 3D circuit boards inside of objects while we fabricate them. And so we did this project together with Autodesk. So we have a design tool that allows you to specify basically surface constraints. I want to connect this place on the surface with this other place. And so we then automatically create the connectivity on the inside of objects. And you can do this with kind of arbitrarily complex geometries. Now, when we did this project, actually, we didn't have a printer that could do this. So, and most people today still don't, right? They still only deposit a single material out of plastic. And so I think one of the themes we found out is it's really fruitful to combine automatic techniques up to the level you can with some instruction for manual steps that makers do afterwards, because they're already handy. They want to be involved in the creation of the object. So in our case, actually, instead of wires, what we create are hollow tubes. And so once something is printed, you can then take a syringe and fill all of those tubes with conductive epoxy, silver nanoparticle ink, any number of conductive materials that'll cure. And so then you've basically, through one automatic step, created the geometry with all the cavities and tubes, and the second step is you then fill it with conductive material. So there are a bunch of different examples we created. For example, this uses Disney's swept frequency capacitive sensing, where you only attach one wire to an object to sense a whole number of different touchpads. We've also created you can use the same approach to create neon art, where you constrain the path of the tube you create to some graphic that you import. And so you can create something that looks like neon art but doesn't require the bending of glass with blowtorches. Now, since we did that project, actually, we're looking a bit into the future. Turns out we didn't have to look all that far. Now you can buy this printer called Voxelate, which in addition to a nozzle also has a syringe that will deposit conductive material. So you can now actually do this without the manual post-processing step. And that tool is now in Autodesk's Mesh Mixer, which is their free mesh munging software. All right, so then let me take a third run at this project by saying, OK, so either we can snap in additional components, or maybe we can just print the connectivity inside the object. What if we just change the paradigm altogether, and instead of putting all these different components in different places, we use a single supersensor to do all of the input sensing at once? So this is what you saw in the beginning, right? So what if we printed out a game controller like that, and then we just take one single powerful sensor, in our case a camera, put that into your 3D printed object, and as soon as you add that sensor, all of the different input affordances on the object start to work. So this is the Sauron project. How this works is this is a plugin to CAD software. So here we assume that you have some familiarity with CAD. We use SolidWorks. You can really substitute any CAD software. And so you model the thing you want to create, and then you add into your model one more object, and that's a virtual camera. And the virtual camera basically matches the size, shape, and optical parameters of a physical camera we have. So you take that virtual camera, somewhere on your object you create a port where it can fit in, and say, I want it to go there. And so that cone is the field of view of the camera. And so you can tell right away everything that's in the cone of the view of the camera, we can now see and sense with kind of off-the-shelf computer vision algorithms. Unfortunately, you can't see everything, so you have to be a little bit smarter. So we have a range of techniques. So camera here is in green, field of view in blue. There might be things that just don't fall into the field of view, right? Like this button on the side. But the key realization here was that we haven't printed this thing yet. That means we can change the geometry to make the computer vision problem easier on us. So in this case, we can just take that button and extrude it until it meets the field of view of the camera. So here's an example of, kind of the extreme case for that technique. So you could actually only see one of those buttons, but we can extrude all of the others to fall into the field of view. Now, that may not always work. So here, for example, a straight extrusion won't get us into the field of view of the camera. In this case, we just take a little bit of computer graphics. So we do ray tracing. We shoot rays from the camera into the scene and look for places where if we bounce the ray off of the internal surface of the object by its surface normal, it'll hit a component we want to see afterwards. Why do we care about those places? Well, it turns out if you glue a mirror into that place and then put the camera in through the mirror through one bounce, you can see the component. So this is yet another instance of this principle of if you add a little bit of manual tasks afterwards, but you tell people what to do and where to do it. So here, take a 25-cent craft mirror, glue it in that place. You can extend the usefulness of your techniques. So then you print the object, and then comes the highly technical step of creating markers for computer vision. So we just paint them on. You can also take a multicolor 3D printer that will do this for you. Unfortunately, that right now still involves paying 10 times as much for that two-color print. And then you add the camera in. And basically, the next step then is running computer vision. So we do this interactively. There's a calibration step where we basically highlight something in CAD and say, just move this component through its range of motion. And so in this case here, we'll just do blob tracking and find the minimum and maximum coordinates. For some of the other components, we don't do blob tracking. We do optical flow. And so there's basically a computer vision algorithm paired with every type of input device. All of the computer vision algorithms are off the shelf. Because the fundamental insight here is, instead of coming up with a better algorithm we come up with a better environment so that existing algorithms perform better. So we've built game controllers, mice, DJ controllers. We had other people build DJ controllers to convince ourselves that this is not only something only the authors can do. And we also went through basically online repositories of models, downloaded the models, and checked which of these models could you actually sense with this technique. And so many of them work. What doesn't work is if you have very small devices and devices that have interactivity around thin features, because a single bounce of light won't get you there. OK. So the key ideas in this project use vision sensing on the inside of fabricated objects. And there's this co-design of the geometry and the sensing technique. So we can modify the shape to create an easier vision problem. This is basically the flip side of the coin of how computer vision usually proceeds, where we say, we don't know anything about the environment. We're going to write smarter algorithms to extract more information from the environment. Here, we control everything about the environment. We fabricate it, right? And so we can use that knowledge to increase the utility of existing vision algorithms. All right, let me at least tell you about one more project and then maybe open it up to questions. So in the prototyping tools, in some sense, we're creating black boxes, right? In that we're letting you author at a higher level of abstraction without you having to understand what the underlying vision technique is. Now, I think that's useful for part of the tasks in supporting makers. But in others, you really just want the makers to grapple with the complexity of what's going on and understand it so they learn and become more proficient. So here we're working on better learning and debugging tools. This is work in progress, so not quite complete yet. In particular, we became interested in helping people breadboard circuits. So the solderless breadboard has been around since the 1970s and was kind of this revolutionary step that you could create working circuits without wire wrapping or making permanent connections. So it actually is a great prototyping tool in itself. But it has a whole bunch of issues. So who's breadboarded circuits in this room? OK, so yes. Then this should look familiar, right? There's this complexity that appears pretty quickly. And then troubleshooting becomes very difficult. A simple thing like a single loose wire, if you can't easily find out where it is, can take you a lot of time. There's also issues like power. Am I powering my components correctly? Have I inserted them with the correct way around? Polarity. Have I connected the right wires to the right pins? Are all my components working, et cetera? So just for reference, this is what a solderless breadboard looks like from the top, right? This is what it looks like from the bottom if you kind of peel away the adhesive that's usually there. So you have vertical connections on the power buses and then horizontal connections. So everything on one row is connected to the middle, and then everything here is connected. Now, if you want to debug your breadboarded circuit today, the usual mode you do that is by coming up with a hypothesis of what might be wrong, then breaking out your measurement tool, like a multimeter or an oscilloscope, and then doing a point-wise measurement to check if, according to your hypothesis, I would expect measurement X. Do I see that or not? And you can either do that just on voltages, or you can do it also instantaneously, or you can do it over time with an oscilloscope. Now, our research idea here is point measurements require a working hypothesis about the problem. We know from studies of how programmers debug that non-experts are not particularly good at generating correct hypotheses initially. And so the idea is let's replace point measurements with ubiquitous instrumentation where we just measure everything all the time. And show you those measurements, but also combine the real-world measurements with some model of the circuit to diagnose what a problem might be. So here's that idea implemented. This is the toast board, the better breadboard. And we basically have instantaneous voltage measurements on every row, running at about 4 hertz right now for the board. And so initially, you can just see immediately what voltage does every row have. But then if you do a little more work and you create a virtual model, like a schematic of your circuit, right, then we can compare what we know about the circuit with the measurement and say, well, this LED looks broken because the voltage drop is unusually large. You should have a voltage drop of less than 2 volts across the diode. So either you've inserted it backwards or it's broken, right? And you can show other information, like here's the current through your resistor, other things that you can then deduce from the measurements and a model of the circuit. So the way we make this work is we take a breadboard and then put it on our own circuit board, and we have a multiplexer scan chain where we basically scan every row of the breadboard round robin. That gets connected to a microcontroller, which drives these LED indicators on the board, but also forwards all of that data to our software. So not sure you can tell much by this board, but what's just a little detail under the hood is how do we make all of those connections? Well, we have a circuit board where you put your breadboard on here. So you peel back the foam, and then you put it on top of these pads. And we use Z-axis transfer tape, which is adhesive that has tiny spheres of conductive material embedded in it, which means it only connects in the Z-axis, but not X and Y. So you just take a single strip of that tape, put it over the board, put the breadboard on top. And then there are some mechanical issues that I'm glossing over, but that's the gist. And so then what that lets you do is debug all kinds of problems, either through just simple inspection of the voltages or through these smart hints that we layer on top of it. So for example, here, if you connect this circuit, right, there's a wire that connects the resistor to ground. Well, there should really only be 1 row lit up here. The fact that there are 2 rows lit up tells you that, oh, you probably didn't put the wire into the correct row. And similarly, we can then also run a higher level check, which says there is no current through this resistor at all, so you probably didn't connect it to your circuit. And so we're still exploring what the set of checks is, what the set of automatic feedback is that we can give you. Importantly, also, right now, we only handle standalone circuits, not circuits that then have Arduinos, .NET, Gadgeteers, general microcontrollers connected. So that's kind of a whole other big area of open questions. OK, it is 10:50. Why don't I skip ahead to some takeaway messages and then open up to a couple of questions. So I think across this research program, a couple of key themes emerge for me from the user's perspective. One, in the prototyping work, right, you really want makers to describe their goals at a higher level of abstraction and then let tools take care of mapping those goals to the really detailed design work, like generating bosses and cutouts and manipulating vertices. There is this distinction of whether your tool is a black box or a glass box. So I think in prototyping, doing a black box is often fine. But when the complexity is inherent in the task and you want people to learn about it, right, then you actually want to show a lot of information and guidance, like in the debugging work. There's this higher level story of getting more utility out of digital fabrication by intelligently combining automatic and manual processes. And then, this is something I didn't show you, receiving guidance through examples and tutorials. Now, a couple of key technical themes here are the projects students work on in Jacobs Hall, in Makerspace's Fab Labs, integrate mechanical, electrical, software questions of use, questions of aesthetics. So our design tools should kind of take this integrated approach as well where possible. And given high-level specifications, co-design sensing and geometry, like things that usually live in different worlds, right? Combine them together. Combine computer vision, AI, digital signal processing techniques for recognition with geometrical design. I showed you this with computer vision. We've also done this with sound, where you print shapes that you know when they're struck vibrate at specific frequencies, and that means it's very easy to create an audio classifier based on that. For the debugging work, it's really ubiquitous sensing, right? Work with rich real-world data and import that into the design environment. And then something that we're really interested in that turns out to be quite hard is 3D scanning has also come down in price, but you barely ever see 3D scanning used productively in makerspaces today. And that is because what comes out is just this mass of noisy data, and then you say, here's your 3D scan, now please deal with these million vertices. And so making 3D scanning a productive ingredient in the Fab Lab tool chain kind of requires abstracting away from dealing with vertices and pixels, and really is about a higher level of understanding. What do you want to do with this object? And then that algorithms take care of all the geometry modification. Future outlook here, I think there's really interesting work right now being done in material science that is filtering into the maker movement. So like conductive materials, printing multiple materials at the same time, printing at 10 to 100 times the speed. And so I think that will be an area where we'll see lots of interesting work emerge. I think physical construction and debugging tools are kind of ideally suited for augmented reality applications. That includes, but is not limited to, head-mounted displays. Right? I think there's a lot of work that can be done that we started to do with integrating projection into handheld tools. And we're using Jacobs Hall as a living lab to deploy and test all these tools. And I think you could also use Mike Sinclair's shop around the corner also as a place to deploy tools like this. Should make sure to give credit where credit is due at the end, in that all of this work was actually done by a fantastic set of students, and I just get to talk about it. All right, thank you. Yes?
Which of these tools do you think extend to experts? That would be useful for experts as well?
So depends on what kind of experts. So for example, the prototyping tools also were informed by my work with professional product designers who do a lot of prototyping, and they're experts in the design process, but they're not expert-trained electrical engineers. Other than that, do they transfer to expert software developers, expert electrical engineers? I think this idea of integrating the concerns you're investigating across different domains, software plus electronics, electronics plus mechanical, that is, I think, right now also a big topic at places that make professional design tools like Autodesk, like National Instruments. And so maybe the particular techniques don't apply, but the larger approach of thinking across the different domains, that is relevant to experts as well.
So I had a question about the prototyping tools, and I feel like it's like a chicken and egg problem, right? You want to create prototyping tools to help makers make what they want to make, but you don't know what they want to make because they don't have the prototyping tools to know what they want to make, right? And so you talked a little bit about like some of the preliminary studies you had done with them. So how do you go about? Can you talk a little bit more about that? Like how you go about understanding sort of what they want to be able to build, and so you know what tools to support to create.
So hanging out in those spaces is certainly a good first step, and observing. And also, I think there's a whole bunch of kind of remote formative work you can do by looking at what happens on places like Thingiverse, on Instructables, and you do get this differentiation that there are some lead users who usually have more experience, maybe because of their professional life, who then push the boundary of what can be created, and then you can maybe look through, do those projects resonate with the larger community in terms of those are the kinds of things other people would want to build as well. But you're right, if tools don't just make things easier, but they make new things possible, there is a bit of the challenge of what you want to have that's possible. So in the class that I teach called Interactive Device Design, we approach that with a quite standard need-finding design process where we send the students out and say, you can propose anything in this class that is an interactive device, but you have to demonstrate that you found a user, talked to them, and understood what some of their needs are. And so that leads to a wide space of different ideas of what our students want to build for others, which is not quite the same as what do I want to build for myself at home.
So you kind of talk about like these tools which help you integrate like form and function together in the same process. Like where do you see is the future when you want to like test out and alter the form? Because like when these two are separate, you still have the opportunity to work with them and get the form right and get the functionality. And so can you talk a little bit about that?
Yeah, so one limitation here is that this process, compared to iteratively modifying software, this process is still kind of slow, right? And so I think, so you made something and then it's not quite right. How do you then incorporate the changes into the next design iteration? So yeah, that's an interesting question. So one thing that's actually happening is maybe the machines will catch up to the speed at which we can think about modification. So for example, we just started printing on a carbon 3D printer at Berkeley, which it's a material science innovation of controlling the amount of oxygen you have at the layer where you do photopolymerization. So anyways, lots of details. The outcome is you can print something this size in 15 minutes. And so once you're at that speed, then it becomes feasible to do lots of physical iterations. The question is how you express the intent of how things should be changed. I think that's an open question, right? Can you maybe print in malleable materials? Or can you then annotate on top of the printed object itself what you want to have changed? So there's some great work from François Guimbertier and Hyungyang Song from about 10 years ago of basically printing out objects and then just writing on them and interpreting that as modifications. There's also some great work by Stephanie Müller out of Germany, who's going to MIT, who's also really trying to shrink down that cycle time for interactively modifying these physical products. So maybe some pointers how that's going to happen.
Okay, I think we'll end it there so we can switch over to
Yeah.
the next speaker.
All right, thank you.
Thank Bjorn.